Have you ever looked at art and wondered, why does it look so realistic? For instance, take a look at Leonardo da Vinci's Last Supper. Look at this painting. There are lots of things striking about it, but one is that it looks like it has depth. Why is that? What are some features that cause the illusion of depth? This work uses the method of what's called one-point linear perspective, which became popular among Italian Renaissance artists as a means of creating the illusion of depth. Do you see how all the lines that go off into the distance appear to converge on a point? Look at the lines where the walls meet the ceiling, and the lines on the floor, and the edges of the table. If you extend them, they all converge on the so-called vanishing point. This is the point on the horizon where parallel lines appear to converge because they go off into the distance. Da Vinci uses this effectively to draw attention to the central figure in the picture, Christ. Notice how his head is placed at the vanishing point. There's geometry in this picture that makes it look realistic. The mathematical ideas behind perspective geometry come from linear algebra, and if we understand it, we can produce realistic computer graphics. Many virtual reality games involve moving around some virtual environment. How can I get a computer to realistically draw such environments? When I move around a room, my perspective of the room changes. I'm actually looking at a two-dimensional projection of a three-dimensional room. So a square carpet may look like a parallelogram if viewed from the side. And in Lecture 1, we saw that this change in perspective acts like a linear transformation, though we didn't say much at that time about what that means. We're going to try to explain that carefully in this lecture. If you're writing a computer program to move around a virtual room, you'll need to be familiar with linear transformations because they are the backbone of machinery used in computer graphics to make realistic projections of three-dimensional space. For instance, rotations and reflections are linear transformations. How do I represent these geometric ideas algebraically so that my computer could accomplish these transformations on a particular picture? We shall see. First, we need to develop some terminology for working with functions. A function is any machine for turning an input into an output. We are mostly concerned with the case where the inputs and the outputs are sets of numbers, which we can think of as vectors. Perhaps the inputs are like a vector of quantities, like grams of nuts and chocolates, and the outputs are numbers, like calories of carbohydrates, fats, and protein. That would be a nutrition function from R2 to R3. You could also have a function going from R2 to R2. An example would be a function that moved points around a plane. You can also have a function from R3 to R1, such as a temperature function, whose input is a position in the room, and the output was a single number, temperature. So we're going to write T colon Rn arrow Rm to signify that T is a function taking an n-dimensional vector to an m-dimensional vector. A function is also called a mapping or a transformation. And a function t sends a point x to the point t of x, which we call the image of x. This terminology also applies to whole sets. The image of a smiley face is where the function t sends the entire smiley face. And if the function is continuous, the image will look like a warped version of the original set. The set of potential inputs to a function is called the domain of a function, and the set of potential outputs is called the codomain of the function. In this case, the domain is Rn and the codomain is Rm. If t is a function, then the range of t are all the points of the codomain that are actually images of points in the domain. The range may or may not be all of the codomain, but if it is, we say the function t is onto. I know it's strange to use a preposition as an adjective, but that is how we use the word. Another term you often hear is the idea of a function t being one-to-one, which means you can't have two distinct points in the domain getting mapped by t to the same point in the codomain. Or, to say it another way, if t of x and t of y happen to be equal for 2 points x and y in the domain, then x must actually be equal to y. For example, think of a function from living people to their last names. The domain of this function is the set of all people. The codomain of this function is the set of all possible last names. The range of this function is the set of last names in use by living people. This function is not onto if there are some last names that are no longer in use. This function is not one-to-one because there are many people with the same last name. Now, not all functions are going to be linear transformations. So let's talk about what additional properties a linear transformation must satisfy. We saw in Lecture 1 that the idea of a linear transformation is a central idea in linear algebra. There we also encountered the definition of a linear transformation, which we explore in greater detail now. If you look at how we use vectors, you see that we often do two basic things with vectors. We add them and we scale them by making them bigger or smaller by some factor. We form linear combinations of those vectors. A linear transformation is a function that in some sense plays nice with respect to linear combinations. A function t from Rn to Rm is called a linear transformation if it satisfies two properties. The first is that t of u plus v equals t of u plus t of v for all vectors u and v in Rn. This first property means that if you add two vectors and then transform it, you get the same thing as if you transformed the vectors first and then add them. We sometimes summarize this property by saying a linear transformation preserves the additive structure of vectors. The second property of linear transformations is that they preserve scalar multiplication. T of c times u equals c times t of u for all scalars c and all vectors u. For instance, if you transform a vector that's scaled by a factor of 5, you'll get 5 times the transformed vector. Taken together, these two properties mean that linear transformations preserve the structure of linear combinations. If I take a linear combination of vectors and transform it, that will be the same result as if I transform it and then take the same linear combination of the transformed vectors. For instance, using the two properties of linear transformations, we see that t of 3u minus 7v equals t of 3u plus t of minus 7v. And that equals 3 times t of u minus 7 times t of v. So this is where a linear transformation gets its name. It's a transformation that preserves linear combinations. Now that we have the definition, let's explore what properties follow from this definition. Mathematicians like to explore properties of objects so that we can use those properties when we need them, and also so that we will be able to recognize other objects with similar properties. First thing to notice is that if you take the scalar to be 0, then property B implies that t of the 0 vector must be the 0 vector. Note that the first 0 vector is the n-dimensional 0 vector, and the second is the m-dimensional 0 vector. So, if a function doesn't take the 0 vector to the 0 vector, it cannot be a linear transformation. Another thing to notice is that a linear transformation must take lines to lines. To see this, recall that a line through a point P extending along the direction vector d can be expressed as p plus td, where t runs through all the real numbers. If you think of t as time and p plus td as the position of a bug, then the bug starts at some point p at time 0, and as time runs forward, the bug moves in the direction d. Now watch what happens when we apply the transformation t to this line. We'll get t of p plus td equals t of p plus t times little t of d, where little t runs through all real numbers. But this is just the point, t of p plus little t times a direction vector, capital T of d. In other words, you get a line and it passes through t of p and extends along the direction t of d. So the transformation t takes a straight line L in Rn to a straight line L prime in Rm. In fact, you can see more from this discussion. If I look at the line p plus td and then change the base point p to the base point q, the direction of the line is still d, it doesn't change. So two lines p plus td and q plus td are parallel. Then their images, capital T of p plus little t times capital T of d, and capital T of q plus little t times capital T of d, are also parallel because they have the same direction vector, t of d. So a linear transformation takes parallel lines to parallel lines. Now, even more is true. If we change the base point again by the same amount as from p to q, then the image base point changes by the same amount as it did from t of p to t of q. So in fact, a linear transformation must take equally spaced parallel lines to equally spaced parallel lines. This property means that linear transformations must take squares to parallelograms, since the sides must remain parallel, but the angles might change. It also means that equally spaced inputs must lead to equally spaced outputs. When we talked about planets moving in the night sky in the first lecture, remember we called it linear motion if for equally spaced time intervals from looking from night to night led to equally spaced positions of planet in the sky from night to night. So we have a pretty good idea of how linear transformations behave. They must take a grid of squares to a grid of parallelograms, and 0 must go to 0, sort of like in this picture. Now, linear transformations are the nicest type of multivariable function because the outputs will depend on the inputs in a very nice way. Linearity says that if my input changes from v to v plus w, then the output changes from t of v to t of v plus t of w. In other words, if the input changes by a vector w, then the output will change by a vector t of w, no matter what v is. Equal changes in input lead to equal changes in output. That characterizes linearity. If you think back to the nutrition function that takes grams of nuts and chocolates to calories of various kinds, we may not know the actual function that does this, but if you think about how such a function should behave, there are good reasons to believe it must be linear. First, adding an additional gram of chocolate will change the calorie vector by the same amount, no matter how much nut and chocolate has been consumed. So equally spaced inputs, such as adding a gram of chocolate incrementally, lead to equally spaced changes in calories, the way linear functions behave. Secondly, the nutrition function sends the 0 vector to the 0 vector, another sign of linearity. Now, if a multivariable function is not linear, it is often approximately linear. This is one message of multivariable calculus, to approximate multivariable functions by linear transformations. For instance, look again at this function from R2 to R2. It does not send the square smiley face to a parallelogram. However, if the function is approximately linear, the word we use in calculus is differentiable, then small enough squares will get sent to things that are approximately parallelograms, like the nose on this face. In multivariable calculus, you learn that the derivative of a function is a linear transformation, because that's the best linear approximation to a function at a single point. If you haven't learned multivariable calculus yet, that's okay. I was just giving you a preview. Calculus is going to be intimately tied to linear algebra, because the nice things in linear algebra are what we actually use in calculus to approximate other things. All right, now we've seen some properties of linear transformations, but what is an example of an actual linear transformation? Well, here's one, multiplication by a matrix. Suppose A is an m by n matrix with m rows and n columns. Then multiplication by A will take an n-dimensional vector to an m-dimensional vector. So t of x equals a times x is a function from Rn to Rm. And moreover, it's linear. We know from thinking about what it means to multiply matrices that for any scalar factor c and n-dimensional vector v, that a times cv equals c times av. Also, from the distributive property of matrix multiplication, we know that for n-dimensional vectors x and y, a times x plus y equals ax plus ay. So, multiplication by a matrix is a linear transformation. What is really amazing is that there really are no other examples of linear transformations. Matrix multiplication is the only kind of linear transformation there is for functions between finite-dimensional vector spaces. Because every linear transformation from Rn to Rm can be represented as multiplication by some m by n matrix A. So the moral of the story is, to understand linear transformations is the same as understanding matrices. This amazing fact is true because every vector can be written in terms of the standard basis vectors. Recall that the ith standard basis vector, E sub I, is the vector of all zeros except for a 1 in the ith position. Any other vector can be written as a linear combination of the standard basis vectors, because if you have a vector, let's say with components x1, x2 through xn, that can be written as x1 times the first basis vector plus x2 times the second basis vector, etc. Now, if you apply a linear transformation t to this linear combination and use the linearity properties, which preserve the linear combinations, you will see that t of x equals x1 times t of e1 plus x2 times t of e2 plus xn times t of en. Now, the right side of this expression can be represented as matrix multiplication by a matrix whose columns are just the transformed basis vectors. You can check this by just thinking about what matrix multiplication means. This matrix multiplication performs the dot product of each of the rows of the matrix with the vector x1 through xn in succession. This is just taking a linear combination of the columns of this matrix. So we have shown that a linear transformation T is determined by where T sends the standard basis vectors. And to find the matrix that represents T, all you have to do is create a matrix whose columns are the transformed basis vectors. In other words, the matrix records what it does to the standard basis vectors in its columns. Looking at the columns shows you what the matrix is doing to the standard basis vectors. We sometimes notate the matrix representing T by putting brackets around the letter T. The idea that you can find a matrix that represents a linear transformation is really powerful. It means that you can tell a computer how to perform a linear transformation even if all you have in your head is a geometric picture. We can see how powerful the idea is by doing some examples. In the plane, a reflection across the x-axis is a linear transformation because the linearity properties hold. If I scale a vector and then reflect, that's the same as reflecting, then scaling. And if I add two vectors and then reflect, that's the same as reflecting and then adding the two vectors. Now, if I want to represent this reflection by matrix multiplication, I just need to figure out where the standard basis vectors 1, 0 and 0, 1 go. You can see that 1, 0 is not changed by this reflection because it's pointing along the x-axis, and so reflecting about the x-axis doesn't change it. So it just goes to 1, 0. However, 0, 1 goes to 0, minus 1. So form a matrix with the first column 1, 0 and the second column 0, minus 1. This is a matrix A that will actually perform reflection across the x-axis. You can check that A times the vector xy is the vector x, comma, minus y. So now I can tell a computer how to do this reflection. Here's another example, a shear transformation. This kind of transformation keeps one side of a square the same, but it pushes the other side in the direction of the first. So 0, 1, in this case, stays fixed, but 1, 0 gets pushed up by 0k to the point 1k. Thus, its matrix has 1k in the first column and 0, 1 in the second column. Multiplying a vector by this matrix will perform this shear. For a final example, let's look at the rotation of the plane by angle theta. This is a linear transformation. Again, you can check this by checking the linearity properties. Taking a linear combination of vectors first, then rotating, is the same as rotating vectors, then taking linear combinations. So there must be a matrix representing rotation. Which one is it? The answer is, look at where the standard basis vectors go and form a matrix with those vectors as columns. Using a little trigonometric reasoning, we see that E1, the vector 1, 0, goes to the vector cosine theta, comma, sine theta. And E2, the vector 0, 1, goes to minus sine theta, comma, cosine theta. You may wish to pause this video now to verify this. Then we form a matrix with the image of E1 as the first column and the image of E2 as the second column. Now keep in mind the order matters here. This gives a 2 by 2 matrix with entries cosine theta, minus sine theta, cosine theta. And if you take a vector x and multiply it by this matrix on the left, it will perform rotation by theta. What happens if you perform this rotation twice in a row? Well, clearly you should get rotation by 2 theta. But this must mean that the matrix representing rotation by theta, when multiplied twice in a row, in other words, squared, must be equal to the matrix representing rotation by 2 theta. Let's just see if that's the case. The matrix representing rotation by 2 theta is this matrix. But if you square the matrix representing rotation by theta, you can check that you get this matrix. These matrices must be the same. So, if you set the corresponding entries equal, look at what you get. You get the double-angled formulas from trigonometry. That's pretty cool. And this idea that if I perform 2 linear transformations, one after the other, that is the same as multiplying 2 matrices, is really useful. So let's summarize it here. Performing 2 functions, one after the other, has a name. That's called a composition of functions. if t goes from Rn to Rm, and s goes from Rm to Rk, then the function formed by first doing t, then s, is the function s of t of x. Notice how the order of s and t gets reversed in the notation because the way we apply functions is from the inside out. We write the composition as s circ t, where circ is the little circle sign. So what we are saying is that the matrix that represents a composition of s and t is just the product of the matrix representing s with the matrix representing t. We'll return to this idea later. We've now seen that a linear transformation has some special properties. It preserves linear combinations, and that means it takes equally spaced lines to equally spaced lines. Matrix multiplication is a linear transformation, and every linear transformation can be represented as some matrix multiplication. We have seen how to find that matrix as well. In many instances, linear transformations represent many of the kinds of transformations we expect to use if we were coding a video game that needs to move around a virtual room and change perspective. Obviously, rotations are important for that, as are shears, which are like looking at an object but from a different angle. Both of these are linear transformations. But not everything we wish to accomplish in graphics applications is a linear transformation. For instance, translations are useful, but they are not linear transformations. And sometimes we want our views to have perspective, like the illusion of depth in Da Vinci's Last Supper. But perspective art does not send parallel lines to parallel lines. You see that the parallel lines go off into the distance, that they're not parallel, they converge at the vanishing point. So maybe there's a little more to making this scene look realistic than linear transformations. Well, that is true, but not by much. I'm going to end this lecture by giving you a sense of what is done in advanced computer graphics to deal with this perspective. The trick to dealing with lines going off to an infinite distance is to think about something called projective geometry, where we keep track of the scale of an object, how far off in the distance it is. The picture itself is just a projection of something far away to a screen where I'm viewing the image. If I keep track of scale and use an additional dimension to record that, what I get are points represented by a 4-dimensional vector instead of 3. Then, amazingly, it turns out you can represent rotations and translations and deal with perspective using linear transformations on R4. And these are represented by 4-dimensional matrices. So doing these kinds of 3-dimensional transformations amounts to doing linear algebra in 4 dimensions. And you can learn more about this in an advanced computer graphics course.